Okay, welcome back. One of the questions that was being asked by a student was, how would the D flip-flop timing diagram change if we assumed a negative edge trigger? So let me illustrate that. Okay. All right, so this was the problem that we did earlier. If this was a negative edge triggered, so I marked this as positive edge triggered, right? The output is positive edge triggered. It's a negative edge triggered. Let's see how the output would change. All right, so we mark the negative edges, which are right here, right? The down arrows. Actually, be more appropriate to mark it on the edge itself. So right here, here, and here. Okay. Excuse me. So it should change at 2, 6, 10, and 14, right? 2, 6, 10, and 14. So negative edges changes at t equals 2, 6, 10, and 14. Let's look at the values of D, the corresponding values of D at those times. Okay, at 2, D is equal to 1. At 6, oh, sorry. At 2, D is equal to 0. 6 is equal to 1. At 10, it's equal to 1. And at 14, it is equal to 0. So first at 2, negative edge value is 2. It remains at, sorry, value is 0. It remains at 0 until the next negative edge arrives, which is at 6. So if this was 6, let me mark out those edges first. All right, so 6 and then 10 and then 14. Okay, these are my transition points. Okay. All right, so at 2, D is equal to 0, so it will stay at 0 until negative edge arrives at 6. And at 6, D is equal to 1. And so the value of Q goes to 1. Okay, value of Q goes to 1. Now, at 10, which is the next trigger, value of D is still 1. So D transferred to the output, meaning Q still remains at 1. So it's still 1 at this point. The next negative edge is at 14. At 14, D value goes to 0. And so it should look something like this. After 14, the value remains at 0. And that's the answer for Q for a negative edge triggered flip-flop. Make sense? Let me know if you have any questions. Any questions at all? Okay. All right. Well, then let's look at shift registers. Shift registers. Okay, shift registers are so called because it takes the input 1 bit at a time, meaning, sorry, not 1 bit, one clock signal at a time. It shifts it inside the system and towards the output. Plus, it stores the data, and hence it is said to be a memory. Okay, it registers the input and stores it, hence memory. Shift registers are of two kinds. Well, actually, technically speaking, there should be of four kinds, depending on the mode of transfer of the bits. You can transfer either in serial or in a parallel manner. Serial or parallel manner, meaning all bits come either all at once in parallel. If you have a three-bit shift register, taking outputs Q2, Q1, and Q0, 4-bit shift register, Q3, Q2, Q1, and Q0. You take the outputs all at once, or you take it serially. Obviously, the advantage of serial versus parallel is that you only need one data line, versus parallel, you need 8. I mean, you need as many as the number of bits that you want to transfer. So if you want a 4-bit data transfer, then you need a 4-bit shift register. Okay, 8-bit, 32-bit, 64-bit. So all in parallel, you need that many shift registers, which in a normal system nowadays is basically nothing. Serial and parallel, again, that indicate the mode of transfer of the information. Serial is more efficient in the sense that it requires just a single data line. And I don't know about you, but I'm old enough to have actually used serial and parallel ports on desktop computers. Well, all of us do still use serial ports. Where? USB. The name stands for Universal Serial Bus. So a USB port has 4 pins. It has a plus and minus 5-volt line, and there are two other lines for data plus, so D plus and D minus. So if you use a USB charger, it only has 2 outputs, does not have anything for data, just has a plus and minus 5-volt line. Okay, so USB is a universal serial bus. It's the successor to the serial port. The serial port itself, if I remember correctly, has 9 pins. A parallel port had about 25 to 30 pins. Parallel ports were used to send information to printers. Serial ports were used to interface many of the instruments that you see on the lab benches. Nowadays, of course, it's just USB. But if you look at any older instruments, they will have a serial port in the back. And that's how we used to communicate instruments, connect instruments via the serial interface. Okay, so this is an example of a serial in and a parallel out. Now, when I said 4, what I meant was your input and your output could be crossed. In the sense you would create a 2x2 matrix. Your input's going in a serial fashion, output's coming out in a serial fashion. So it's serial in, serial out. If you take the output as parallel lines, then it's serial in, parallel out. It's 2 in 1. Case in point, if your input is going in this direction, you can take the output from Q3 in a serial fashion. Okay, so serial in, serial out. But if you take the outputs of all flip-flops in that system collectively in parallel, which is possible, so you have Q0 to Q3, a 4-bit parallel out, then the same shift register is a serial in, parallel out. Okay. You also have a parallel in and serial out. Okay, parallel in and serial out. And similarly with this one, similar to this one, you can still take parallel inputs and parallel outputs in the same system. Also, I'll come back to this slide, but I'm just speaking of the parallel in, so I just want to show this. You have parallel data inputs. Oh, sorry. You have parallel data inputs at the top. You have 4 flip-flops, and it is not shown here, but obviously it is possible to take parallel outs. And I'll come back to this slide later. Okay. So this is just an example. Two shift registers, serial input, second shift register, parallel input. In both cases, both shift registers, doesn't matter what the input transfer is, whether it's serial or whether it's parallel, the outputs can be both serial as well as parallel. Okay. If you take the output serially, parallel in, serial out, take it parallelly, it's parallel in, parallel out. So I would say these outputs, let me just mark it this way. Parallel outputs in the same shift register. All right, let's go back to our first one. What do we see? We have 4 D flip-flops. 4 D flip-flops. The output of the first one goes as input to the next. So Q0 goes to Q1, Q1 goes to D2, Q2 goes to D3. If you had 4 more bits, meaning an 8-bit shift register, then the output Q3 would go to D4, Q4 would go to D5, and so on and so forth. Okay, so the output of the first one is shifted to the next upon the arrival of the clock signal. Okay, so it's serially fed in a sequence. Clock inputs are all tied together. This is the fundamental principle of why we use a clock signal. So we synchronize all systems, all components of the system to one single clock. Okay, so this is a synchronous system, which basically all computer systems that we use are synchronous. Okay, so the clock signals are all tied together to one single clock input. The data input is connected to the data output of the previous flip-flop. So here's the timing diagram. Here's the clock. Positive edge or negative edge? Bubble or no bubble? No bubble. So positive edge. So positive edge triggers. The first thing I would do is I will note the positive edges of the clock. So again, timing diagram. If you're reading the timing diagram, if you're looking at the timing diagram, you're reading it, then you always want to first note whether the flip-flop is positive edge triggered or negative edge triggered, and then note all the edges in the clock signal. Okay, in the clock signal. All right, so positive edge triggered, and then we look at the data input that's coming to the first flip-flop. Okay, this is the input to D0. D0. And again, D flip-flop simply takes the input and sends it to the output upon the arrival of the trigger, the clock trigger. So data input remains at 1, but the output doesn't change until the arrival of the positive edge trigger. On the arrival of a positive edge trigger, the 1 is sent to the output. So Q0 goes to 1 right here, the positive edge triggered. It's the negative, it's the positive, positive, and positive. So it's 1, and then here it's 0, here it's 1, and then here it's here again it's 1. Okay. So every time the edge trigger arrives, I'll note it in the clock, and then I will note the value of the input at the moment the edge trigger arrives. And then that is transferred to the output. So it goes to 1, the first, then goes to 0, goes to 1, then remains at 1. Okay. So first transition, D is equal to 1. So Q0 goes to 1. Then Q0 remains at 1 until the second transition. At that point, it changes value because now data D is 0. Then it will remain at 0 until the third edge trigger arrives. When the third edge trigger arrives, output goes to 1. The fourth edge trigger, data input is still 1, so the output remains at 1, and hence we have that long line at the end. Make sense? Right? So that was for Q0. But the output of Q0 is fed as input to D1. And so we have to look at what happens at the output for Q1. And Q1 will remain at 0. The transition is here and here. Only 2 edges. Okay, only 2 edges. Sorry. That's incorrect. Not transition. This is not the counter. This is the shift register. So the edge transition still remains the same. It changes in value right here, and right here. At least it's triggered in value. Okay. All right. So it's supposed to change values, transition at this point, and at this point. Okay. All right. Let's take a look what Q1 will be when Q0 is 0 and 1. So first transition is right here, second is right here, third is here, fourth is here. That's not the T value, okay? That's just the transition. So the first transition, Q0 is 0. Q1 doesn't change because this remains at 0. Q0 remains at 0. Okay. Now, when the next positive edge arrives, it goes to 1. Okay, goes to 1. Again, it's a D flip-flop. It simply takes the input, sends it to the output. Then goes to 0 here, goes to 1 here, and this is then fed as input to D2. Okay, fed as input to D2. So D2, output Q2 remains at 0 until the positive edge arrives. When the positive edge arrives, it's going to shift. And we get a waveform like this, which is then fed as input to D3. D3 remains at 0 until that positive transition. Then it changes value, goes to 1. Okay. The arrows that you see here, that simply indicate that the output of each flip-flop is acting as input to the next one. And so it's shifting the input data in a step-by-step manner, hence a shift register. It's also going in a serial fashion. It's a serial input. Okay, serial input. All right, questions? Let's see, shift register, serial in, parallel out, and then parallel serial ripple counter. Actually, we covered it. Makes sense? Okay, then let's simply look at the parallel and serial out. Works in a similar fashion. The only thing is, doesn't matter what the input is, they're all connected via AND gates into the input of the flip-flop. And what it does is, it's connected, the output of the AND gate is connected to the preset. What does preset do? Preset actually sets the output to, anyone? As preset and clear. Clear changes the output to zeros. Preset means you're presetting the output to 1. So preset is 1. Meaning, if this goes 1, outputs all go to 1. Meaning Q0, Q1, Q2, and Q3 all go to 1. Okay. So you have parallel data inputs all coming in, and they're all connected to the preset button via an AND gate. Okay. So let's take a look at how this is going to work here. AND gate, multiplication, output goes high only when both inputs are high. It's 0 and 0, 0 and 1, 1 and 0, 1 and 1. So if any one of the inputs to the AND gate is low, meaning it's 0, then the output goes to 0. For the output to be 1, both inputs to the AND gate must be 1. So we tie one input for each AND gate together and call that input as parallel enable. Parallel enable. If parallel enable is 0, the output of all 4 AND gates will be 0. Okay. So parallel enable, if it's 0, all preset values would be 0. Enable needs to be 1 in order for the inputs, output of AND gates equal to 0. And here, AND gates will be equal to A, B, C, D. Okay. If parallel enable is 0, it doesn't matter what values A, B, C, D have. The output of the AND gates will all take 0 values. If parallel enable is 1, then the output of the AND gate takes the values of A, B, C, D. A, B, C, D itself can take only 2 values, 0 or 1, right? So if A, B, C, D is 0, output of AND gate is 0. If A, B, C, D are 1, 0, 1, 0, the output of those AND gates are 1, 0, 1, 0. Whichever gate output is 1 will set the D flip-flop output to 1. So it doesn't matter what the input is, the output will remain at 1 because it's preset. Okay, it's preset. So depending on the clock signal, so there are a lot of inputs here. There's parallel enable, there's a serial input if you wish to use it as a serial register, right? If you wish to use it a parallel register, we simply take the inputs, feed it into the preset button of the flip-flop, and the output goes to 1. Another input is the clear input, which is at the bottom of the flip-flop. If clear goes 1, it doesn't matter what any of the other inputs are, output goes to 0. Again, as a refresher. Preset, meaning output is set to 1. Clear means output is set to 0. It's clearing out. Okay, clear means output set to 0. Reset means it's set to 1. So the difference between the two registers is basically nothing, exactly the same. The preset and clear are not shown here, but again, they are present on every flip-flop. Okay, so there's no difference. Both shift registers are exactly the same. The only difference is if we wish to feed all of the data in a parallel fashion, then we take the serial register and give all 4 inputs or all 3 inputs or all 8 inputs, depending on how many bits you have, via a AND gate and feed it in a parallel fashion to that shift register. Okay, I'm going to send all of the data all at once into those flip-flops, right? The whole point is, instead of waiting for data to arrive bit by bit, all of the bits are already present at ABCD. You enable, parallel enable goes to 1, then all of the data goes instantly into those flip-flops. And that's it. Parallel inputs. Make sense? Hopefully. All right, let's take a pause, think over it. Let me know if you have any questions. Any questions at all? Nope. Okay. These are basically the building blocks for memories that we use. Right? As long as power is applied, the output of those flip-flops do not change. They stay the same. Okay, well, I will say that that is the end of chapter 4. Chapter 5 on Friday, mostly a theory-based chapter about microcontrollers and microprocessors. We'll take these building blocks of digital logic circuits, and we can create big, larger circuits that we use today. Okay, so it's only 11:30. It's still open, chapter 5. Chapter 5 is not going to be very long anyway. Computer architecture. All right, let's just end class here today, and I will see you on Friday for chapter 5. Take the rest of the time and, well, study and complete the homework. I'll be available if you have any questions. Excuse me.